Good morning, everybody. Welcome to a Wednesday morning of Chem 1211 with your host, me, Dr. White. Hi, everybody. All right, want to start out with some important announcements. And let's go to Blackboard. And I mentioned it yesterday, but I don't know if I stressed it enough. In student view, this is Lab 6, which I covered yesterday. It's due next Tuesday. You will not use anything from your chem kit. And actually, you will not be doing any actual experiments for this lab. You will use the provided data to complete the lab report for this lab. So you're not going to do any mixing. You're not going to burn any nuts. You're just going to use the data I provide to write the lab report. All right, another thing, because a couple of you got your kits very late. I have opened all the labs 2, 3, 4, and 5. So if you haven't handed it in, you can hand it in. And think of this sort of as a lab amnesty program. Now, if you're late and you did have the kit, well, I'll tell you what, I won't take any points this time, but this is the only time of the semester. I like that special effect. The only time I'll do a lab amnesty. But get your labs in. Most of you have. I appreciate it. I didn't have time yesterday, but tomorrow I'll catch up in all the labs except the one you handed in yesterday, even yesterday, maybe by Friday, I'll have up to date your lab scores. Looking at what am I supposed to do today? All right, let's get to work. Now, yesterday, we went through and I talked about how the coefficients, actually Monday, the coefficients in an equation give fixed molar ratio between the substances consumed and produced in a chemical reaction. Now, before I go back to this, I was thinking this morning, I do that sometimes. Oh, that was a bad joke. Sorry. Let's go back and review a couple important things. And let's look at the following. And this is an important skill you should have. Hint, and that is how many grams of water are 7.34 times 10 to the squared moles of water. So what I ask you to do right here is put down what are you being asked to find, the units, what are you given? When you're done, give me a thumbs up. And everybody's done, so my turn. And what are we being asked to find? I like to put a question mark there, grams of water. What are we given? This. And therefore, this is the only thing we have to work with. So I'm going to start with that. Now, if there were a ratio, I could convert it to my answer My answer units would be, as we figured out right here, grams of water. Now, I'm going to let you figure out what units you put on top and below that ratio. Not asking numbers, just the units. Use your good buddy, your good friend. And when you're done, give me a thumbs up like one of your colleagues has already done. And you're all done. So how do we figure out what goes on top and bottom of that ratio? Use your good buddy, your good friend, unit analysis. And it has been my good buddy and good friend for many, many decades. Wow. Anyways, whatever you're trying to get to unit wise goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And I'm going to write that right now. And where do we get these numbers? And I haven't had a chance to change it. By Monday, I will. You go to important information, test number 1, and you see 1 mole of a compound equals the molecular weight of that compound. And the molecular weight of that compound is the sum of all atomic weights. So we now need the molecular weight of water in order to use this right here to get the numbers that go in that ratio. So how do we do that? We look at the periodic table, and remember on next test, or the first test really, and my quizzes, it will now say under your name, please use proper significant figures for all calculated answers, and please use all atomic weights to 3, yes, 3 significant figures. And hydrogen to 3 is 1.01, and oxygen to 3 is 16.0. So we now have to figure out the molecular weight. And for water, there's 2 hydrogens and 1 oxygen. And each hydrogen, as we just saw, has this atomic weight. Each oxygen, which there's only 1, has this. Now, we'll do the math. Add these up because the molecular weight is the sum of all atomic weights. And when you're adding, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. And this has 2, this has 1, which is a smaller number, 1. So here's my decimal point. Here's the first one I keep. This is I use to round off. It's 4 or less. So the molecular weight of water is 18.0. Now, 1 mole of a compound equals the molecular weight of that compound. So now I know for every 1 mole of water, there's 18.0 grams of water. Now, before I pick up my my calculator, which I'm going to take off the shelf right now, I'm going to check and see, are my units going to give me the right answer? And if I come over here, I have moles of water divided by moles of water. Remember, anything divided by itself equals number 1, meaning it's canceled out. That cancels out. I'm left with grams of water. I'm on the right track. So now I'm going to pick up my calculator, clear it. I always do. 7.34 for this calculator to get 10 squared, second key, double E. You see the E on there, you probably can't see it. Put a 2 in there, multiply it times 18.0. And my calculator gives me this number. But I know when I multiply and divide, I should get the same number of significant figures as the number with the lowest significant figures that I'm multiplying and dividing. This has 1, 2, 3 significant figures. Remember, all non-zero numbers are significant. This has 1, 2, but zeros at the end with a decimal point are significant, so that has 3. Now the 1 is part of the definition, so that's an exact number, plays no role in there. And now I know this should have 3 significant figures, which means you got to round it off. So I'm going to give you time now. Why don't you round that off to 3 significant figures? And I will then. All right, let me do it now. Well, I'll give you another few more seconds. All right, my turn. Now, how do we round it off? Keep the 1, keep the 3, keep the 2. That's my 3 significant figures. The next number I used to round off, that's 4 or less, so I'll drop that. So this becomes 1.32. You don't change the power of 10 grams of water. And that's how you do that. Let's do another one. And the question is, and I might even make this 8 points sometime in the future. How many moles of ammonia, and NH3 is ammonia, are 2.475 times 10 to the 6 grams of ammonia. And since we're going to do it stepwise, I'm going to ask you, what are you being asked to find? What are you given? And again, we're going through some important stuff, and a little while before the end of this hour, you'll find out why I'm going back and doing this. And all I'm asking you to do is find out, what are you being asked to find? What are you given? All right. Now it says how many moles are, so we're trying to find moles of ammonia. What are we given? 2.475 times 10 to the 6 grams of ammonia. And now, once we do this, we never have to look up at the word problem again. Now, the only number I have to start with is this. if I had a ratio, what units would I want over there? And what units should go up here and here? I'm going to let you do that, and don't put the numbers, just the units. So you got to do three things. What units go here, and what units go on top and bottom? Your turn. Use your good buddy, your good friend. All right, my turn. As soon as I wipe up the water dripping from my water bottle. All right, what are we trying to find? Moles of ammonia. How do we figure out what goes on top and bottom? Use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top. The units, whatever we're trying to get rid of, goes underneath. And I'll write that. And where do we get these numbers? From the fact that 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. Well, we've got to figure out the atomic weight of ammonia, which has nitrogen, hydrogen in it. So if we go to our friendly neighborhood, remember the molecular weight is the sum of all atomic weights. Hydrogen, the three significant figures, is 1.01. And now nitrogen, remember that's the number underneath the symbol is the atomic weight, is 14.007. I'll let you round that off the three significant figures. I'll give you 10 seconds. Go. Go. Oh, come on, Dr. White. That's not nice. Please do it now. Give you a bonus 5. Time's up. How do you do 14.007 to three significant figures? Keep the 1, keep the 4, keep the 0 after the decimal because that's significant. The next number to round off is 0. It's less than 4 or less. So I drop the 0 and 7, and to three significant figures, the atomic weight of nitrogen is 14.0. So we need the molecular weight of ammonia. That's 3 hydrogens, 1 nitrogen. 3 times 1.01, 1 times 14.0, sum of all atomic weights. Do the math. Add these up. Remember, when you're adding, you get the same number of significant figures to the right of the decimal as the number that has the fewest significant figures that you're adding to the right. This is 2, this is 1. Lowest number, and time's up. Hopefully you pick 1. Why don't you round this off, and then I will, to 1 significant figure past the decimal. All right, time's up. Keep the 0 because we're doing 1 significant figure to the right of the decimal. That's my 1. Use the 3 to round off. Is that 4 or less? Yes, I drop it. So 1 mole of a compound ammonia equals its molecular weight. And for ammonia, it's 17.0. Now, before I pick up my calculator, I'm going to check my units, because that's also part of your good buddy, your good friend unit analysis. Notice I have grams of ammonia divided by grams of ammonia, and anything divided by itself equals the number one, meaning it cancels out. So this cancels out, and I'm left with moles of ammonia, which is what I want to get. So now I'll take my calculator, clear it, and put in 7.475. Then it's times 10 to the 6th, second key, double E on my calculator. And I'll put in 6. And then divide it by 17.0. And when I do that, I'm laughing because you'll see my calculator gives me this number. That's why I'm laughing. That. Now, when you multiply and divide, you have the same number of significant figures in your answer as the number with the fewest significant figures. And you should be able to figure out this has 1, 2, 3, 4, all non-zero numbers are significant. 4 significant figures. The one mole, is the definition. So that's exact number. And the molecular weight, this has 1, 2, decimal, 0 after decimal, 3 significant figures. And which of these two numbers is lower, 4 or 3? And time's up. Hopefully you pick 3. So now this is not 3. Why don't you round that off? Ooh, this is a tricky one. To 3 significant figures. Your turn. All right, my turn. And how do you round this off to 3 significant figures? You keep the 4, keep the 3, keep the 9. Use the 7 to round off. That's 5 or higher. So all this I drop, and I increase this by 1. Well, that becomes 0.1. So the number would be 4.40, 3 significant figures, times 10 to the 5th moles of ammonia. And like I said, this is a little tricky to round off, but when I increase, think of this as 0.39, increase it by 0.01, and that's how you got that. All right, let's do one more, because you'll see why I'm going over this again. Oops. All right, let's look at the following. And the following is how many moles of O2 are needed to make 8.63 moles of water. Your turn. What are you being asked to find? What are you given? Oh, wait, I see someone. I'm sorry. Which one did I make a mistake?
Maybe I did. I'm just not
Which
sure.
problem? This one or the previous?
This one. No, no, this one.
The one with the, I have 1.32?
No, no, the next one. 1 over 17.0. This one.
All right, hold on. Let me, I can make mistakes too. I have 74, 75 tenths of 6 divided by 17. I get 4.39. Let me do it again. And one of the important things I haven't mentioned, let me finish this first. Nope, I get 4.39705, et cetera, times 10 to the fifth. Now, it's a good question. Like I say, there's no such thing as a dumb question. And it's time for me to say something important. One of the reasons Dr. White doesn't like multiple choice questions, because what if you put the wrong number in your calculator? You set it up right, but you put the wrong number in. You hit the wrong button. That happens. It's happened to me. Well, if you don't show your work, like on multiple choice, and you got two choices and you pick the wrong one, you get all 0 points. However, on my test, I don't use multiple choice for the bulk of the problems, especially like the one we just did. And therefore, if you make a math error, let's say it's 8 points, if you show your work, I'll only take off 1 point, you'll get 7, assuming your work is correct, like I just did. So it always pays on my test. I like those special effects, my test, to show your work. Because if you make a mistake, I can find it and say, oh, that's a minor mistake. And if it's a math error, I'll take off 1 point. Say if another type of mistake, I may take 2 points, maybe 3. But if it's 8 or 10 points, you'll still get the bulk of the points if you show your work. So remember, it always pays to show your work. And if I don't see when you put a message in chat, because I still don't look at it as often as I should, open your mic and ask. That's why I allow people to open their mics. All right, let's go back to this problem. And the question is, what are you being asked to find? What are you given? Thank you, Gianna. Thank you, Hannah. And now it's my turn. And what are we being asked to find? How many moles? O2. What are we given? How many moles of water we want to get, but we're also given the balanced chemical equation. You need that to do this problem. So how do we start? Well, this is the only number I have to deal with, so I'm going to deal with it and use it. And if we use our good buddy, our good friend, unit analysis, if we have a ratio, I'm going to let you do this. What units do you want to get to? And what units, not numbers, units, should go on top and bottom of that ratio? Your turn. Thank you, Hannah. Remember, use your good buddy. All right, I'm gonna say it's my turn now. So it's time to, first of all, what are we being asked to find? And the answer is moles of O2. So we'll put that there. And now it's time to use your good buddy. Oh, wait a minute, let me do that again. Your good buddy. That's better. Your good friend. Oh, I'm going to have to change the batteries on that. Unit analysis. And whatever we're trying to get to goes on top of the ratio, units, and whatever we're trying to get rid of goes underneath. And now, all right, hold on. There we go. Sorry about that. I'll write in the units, moles, O2, moles of water. And where do I get these numbers? From the balanced chemical equation. The coefficients, the number in front, and when there's no number in front, it's the number one, tell you molar relationship. And this tells me 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water, H2O. So from that, I can say for every 1 mole of oxygen, I make 2 moles of water. And this allows you to figure out the problem and what goes in there. Now, before I pick up my calculator, I'm going to check my units. Notice moles of water divided by moles of water, and anything divided by itself equals number 1 canceled out. So this is canceled out. I'm left now with moles of oxygen. And now I will pick up my calculator, clear it, 8.63 divided by 2, and my calculator gives me this number. That's a 5, but this is a multiplication division, and you should have the same number of significant figures in your answer as the number you're multiplying dividing with the lowest number of significant figures. This has 3 significant figures. Now, the coefficients from a balanced chemical equation are exact numbers, which exact numbers do not play a role in determining how many significant figures your answer should be. So the only number I have to deal with, significant, is 3. So now I'll let you round this off to 3 significant figures. I'll give you another 6 seconds. Go. Give you some bonus time. All right, my turn. Keep the 4, keep the 3, keep the 1. That's my 3 significant figures I need. And use the 5 to round off. Is that 4 or less or 5 or higher? Hopefully you pick 5 or higher. Drop that, increase the 1 in front by 1. And the correct answer here is 4.32 moles of oxygen. And remember, the coefficients, the number in front of a balanced chemical equation tells you molar relationships. In this one, 2 moles of hydrogen gas, H2, reacts with 1 mole of oxygen to make 2 moles of water. Now, earlier I said this is one of the most powerful things I know in chemistry, actually the two together, moles and the molar relationship of a balanced chemical equation. Why do I say that? Well, you're going to find out. Now, I hate to break it to you. If we're in real life in a lab, but actually you've got your kit and you've got a balance, there are no balances I have ever seen that you weigh moles. No, 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 none. What you do weigh is grams or weight, such as pounds in America, or grams we use in science, and also in Europe. By the way, because I worked for international chemical companies, 3 of them, and I worked in Europe a lot. In the United States, in chemical plants, they use pounds, but in Europe, they use grams and kilograms. And what I'm going to show you is real life. Let's look at the same equation, chemical equation. And let's do this. Yep, 10 points. All right, everybody see 10 points on your screen? Give me a thumbs up if you can see it. Thank you. All right, let's go through this. How many grams oxygen are needed to make 3.456 times 10 to the third grams of water? Now, I'll let you go right here. You go first. What are you being given? And what are you being asked to find? And when you figure out those two things, give me a thumbs up. Or I guess you could do a thumbs down or any other emoji that Zoom allows you. Oh, I forgot the many. Sorry. It should be how many grams. I don't do that on test, but on a board, I'll do that. All right, my turn. You're being asked to find how many grams of oxygen are needed to make these many grams of water. Now, since this is the only thing I have to start with, I'll start with that. And if I had a ratio, what units do I want my answer to be in? Grams of O2. And I'll use my good buddy, my good friend, to say the units I'm trying to get to go on top of that ratio, and the units I'm trying to get rid of go underneath. And I'll write them in. And I'll say, where do I get these? And now I'm stuck. This does not exist. See, it even says on the screen. There's nowhere I can find a relationship of grams to oxygen to grams of water. It doesn't exist. Oh no, I'm stuck. No, here's what you have to do. And what I call in your book, I think, mass calculations for reactions. Finding the moles of mass of substances in a chemical reaction. And there are 3 steps. Whatever you're given in grams, the mass or grams of A, you have to convert to moles of A. That's the first step. The second step you have to do, moles of A, you convert to moles of B. B is what you're trying to get to molecule-wise or compound-wise. And the third step, you convert moles of B that you just calculated in step 2 to grams of B. So let's do this. So here, since I can't do this, and let me write it down here, because I'll need a lot of room. All right, so step 1. All right, first of all, for this problem, you're going to need 3 steps. Step 1, you're going to have to do grams of A to moles of A. What's A? Whatever you're given in grams. In this case, it's water. And we want to convert it to moles of A. In this case, that's moles of water. So you use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. I'll write that, moles water, grams of water. And where do I find that relationship? And by the way, I should have also pointed out, if you look at, that's the wrong place to look, important information, test number 1, mass calculations for reactions. I will give you that. In the past, students have to memorize this, but I'll do that. Right now, we're doing step 1. And what's the relationship between moles of a compound and grams of a compound. 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. Stuff we just practiced, which is why I had you practice it. So for water, we've already done that. I'll do it real quick. Remember to round it off, and the molecular weight of water to proper significant figures for addition is 18.0. So every 1 mole of water, there's 18.0 grams of water. I'll check my units. Water, grams of water divided by grams of water. Anything divided by itself equals the number 1. That cancels out. And I'm left with moles of water. Now I'll pick up my calculator, turn it on, clear it. 3.456, second key double E, 3 divided by 18.0. And my calculator, interesting enough, gives me this number. And this is 4 significant figures, exact number, 3 significant figures, and this is 3 significant figures. So this is the number of moles of water. Am I done? No, I'm trying to get the grams of oxygen, and you need 3 steps. And the second step is convert moles of A to moles of B. And what's A? Whatever we just found, which in this case is water. What's B? Whatever we're trying to get to. And for this problem, that's oxygen. So what I have to start with, moles of A, is 1.92 times 10 squared moles of water. That's what we found in step 1. In step 2, we want to go to moles of B. And what is B? Well, the molecule we're trying to get our answer for, oxygen. And now I'll use my good buddy, my good friend, and whatever I'm trying to get to, the units go on top of this ratio. Whatever I'm trying to get rid of, the units go underneath. And now I'll write it in. And where do we get these numbers? A relationship of moles of one compound to moles of another from the balanced chemical equation. And this tells me 1 mole of oxygen, actually 2 moles of hydrogen, but we're not using that in this problem, makes 2 moles of water. 1 mole of oxygen makes 2 moles of water. Remember, when there's no number in front, the coefficient is 1. So from the balanced chemical equation, every 1 mole of oxygen makes 2 moles of water. So 1 mole of oxygen makes 2 moles of water. And now notice moles of water divided by moles of water, anything divided by itself is the number 1. Ooh, it's on the board already. So that cancels out. I'm left with moles of oxygen, which I want to get to. So now I'll pick up my calculator. and divide 1.92 times 10 squared divided by 2. And my calculator gives me this number. But let's look at this as an addition subtraction, and we're going to go a little past the break. You'll still get your 5-minute break, but I want to finish this problem. And here we have 3 significant figures, and these numbers from the balanced chemical equation are exact numbers, and they don't play a role. So now we have this should be 3. Oh no, this is only 2. How do we convert that to 3? Put a 0 at the end, and now we have how many moles of oxygen we need. Are we done? No, because up here we figured out we want to get 2 grams of oxygen. And notice we need 3 steps. We've done step 1, we've done step 2, and now step 3, convert moles of B, what we just found out, to grams of B. Remember, mass is grams. Oops. So what is step 3? Moles of B to grams of B. What moles? Well, we just figured that out. B is oxygen, what we're trying to get to. And this tells us we want to get to grams of oxygen. And if I had a ratio that can convert moles of oxygen to grams of oxygen, how would I get there? Use your good buddy, your good friend, unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. I'll write those units in. And where do I get these numbers? Well, you look at the following. 1 mole of a compound equals the molecular weight in grams of the compound, and the molecular weight of the compound equals the sum of all atomic weights. And if I go to my periodic table, oxygen, the 3 significant figures, the atomic weight is 16.0. So oxygen molecular weight, O2, is 2 oxygens. And that's equal to 2 times 16.0, which is 32.0. Because this is 1 past the decimal, this is an exact number. So for every 1 mole of oxygen, there's 32.0 grams of oxygen, gas, O2. And before I pick up my calculator, I'll say moles of oxygen divided by moles of oxygen. Remember, anything divided by itself equals the number 1, meaning it's canceled out, gone. And I'm left with grams of oxygen. And now I can pick up my calculator and put in 9.60 blue double E1 times 32.0. And my calculator gives me the following number. But this is 3 significant figures. This is how many? 1, 2, 0, after decimals significant, 3 significant figures. This is an exact number. Doesn't play a role, so which the lower number? 3 and 3, 3. So I'm going to have to round this off to 3 significant figures. Keep the 3, keep the 0, keep the 7. Use the 2 to round off. That's 4 or less. So my answer, and this is how many grams of oxygen I'll need. Remember, you need 3 steps. Now, I went a little over my break, a lot over. Let's take a 5-minute break. Come back at 10:02. That's about 5 minutes. So let's come back in 5 minutes and we'll continue on. And I'll go over that problem again to show you what I did. Time to get going. All right, now, what I just showed you, that three-step process, why is it so important? Because that's the way people like me, and I have done that. That was part of my job when I worked at different chemical companies to come up, we call them procedures or recipes at one company. I didn't like that name, but they used it. Uh, how many how much weight-wise of different chemicals do you put together to make a product that you use in your daily life? Example, I've done things where I've worked at companies that have made the molecule that's used as a fabric softener, another molecule that's used to kill, it's antibacterial, which was very helpful. I didn't work at those companies anymore, but were used to kill COVID-19 on surfaces of things. And just to give you a quick thing, oh, there's a nice one. All right, everybody see on your screen, like right here, where it says Wabash Chemical Stainless Steel Tank. All right, those are called tank wagons. From the old days when they used to put a tank on the back of a wagon pulled by horses. Obviously, we don't do that anymore, even though one company I worked at, there was a special celebration. This was in Germany. They actually had an old tank wagon that was pulled by horses for the celebration. It was quite exciting to see. Well, why am I showing this? Tank wagons are standardized. Those are also the same ones that bring gasoline to gas stations. They're 40,000 pounds, 5,000 gallons, period. This one over here, they call it a tank trailer. No, it's a tank wagon. And if you notice the ladder on there, that's so you can go up there to make sure it's clean in there. It's not fun climbing one of those in a snowstorm in the winter. Been there, done that. But anyways, the reactions I showed you, the calculations I've done for reactions where you use 180,000 pounds of your final product. That's the same as 4.5 of those tank wagons full. Now, railroad car tankers, they're called, come in different sizes that are much bigger. So let's go through what I just showed you in order to find out, going from how many grams of oxygen are needed to make this amount of water. You have to do 3 steps. You can't go from grams to grams. This does not exist, says it on the screen, must be true. And you need 3 steps. And as I said, important information, you will be given this for test 1. You have the 3 steps for mass calculations. Remember, mass means grams. Convert mass of whatever you're given to moles of that compound. Next step, convert moles of whatever you just found to moles of what you're trying to get to. And the third step, convert moles of what you just found to grams, which is your final answer. So let's do another one. All right, why aren't you going up? Hold on 1 second. There we go. I did it again. This is don't write down the word many Wednesday. All right. So everybody see 10 points on your screen? And how many grams? Maybe you don't. Hold on, I better check. Yep, you should see it. Thank you. All right, how many grams of ammonia are made when you react 8.765 grams of hydrogen with an excess of a nitrogen? So I'm going to let you figure out what are you being asked to find and what are you given. Again, all I'm asking you to find is what are you being asked to find unit wise and what are you given?
I just have a question. So when we have grams to grams, that's just hint for us that we have to do this 3 steps that you just showed us, right?
Correct.
And that's always the same thing, the same procedure.
For this type of problem, yes.
Okay.
And thank you for your question. All questions are good questions. All right, let's do this. You're being asked to find how many grams of ammonia. What are you given? Well, you reacted with 8.765 grams of hydrogen. Now, as soon as you see excess, that means ignore it, because that means you've got as much nitrogen as you need to react with anything nitrogen will react with. So now we're also given the balanced chemical equation. Once we have this, we don't have to look at the word problem again. Now notice we're going from grams of one compound to grams of another compound. And there's no way to go that way, directly convert. So you need three steps. And where do you find those three steps? You look at important information that will be in the back of your test, number 1, and that is for mass. Remember, mass is weight. Calculations for reactions, you need these three steps. Step 1, mass or grams of A to moles of A. That's whatever you're given in grams, you convert to moles. Next, what you just convert to moles, step 2, you convert to moles of what you're trying to get to, compound-wise, B. And finally, step 3, whatever you just determined the moles of, B, you convert to moles, from moles to grams. So let's get to work. So step one, and how do we determine what A is? Well, whatever we're given in weight, and that's the hydrogen. So what we need to do now in one step, go to moles, what's A? Hydrogen. And now we'll use our good buddy, our good friend, whatever goes on, whatever we're trying to get to goes on top of the ratio, whatever we're trying to get rid of goes underneath. And I'll write that in. And where do I get the relationship between moles of a compound and grams of a compound? If we look at important information, test number one, I got to change the name. I haven't yet. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight is the sum of all atomic weights. So now I have to go to my periodic table for hydrogen gas H2. There's only hydrogen, the 3 significant figures, the atomic weight, the number underneath, rounded off, the 3 significant figures, was going to say on your test number one, please round off all atomic weights, the 3 significant figures. That's my gift to you, makes your life easier. It's 1.01. So I know the molecular weight of hydrogen is the sum of all atomic weights. There's 2 hydrogen, 2 times 1.01. And since this is a multiplication, the 2 is an exact number. This is 3 significant figures. My answer, which is 3 significant figures. So for every 1 mole of hydrogen, there's 2.02 grams, the molecular weight of hydrogen gas. Remember, we're talking about H2, not hydrogen atoms. Now, before I pick up my calculator, I will say, do my units cancel out to give me the right answer? Notice grams of hydrogen divided by grams of hydrogen, anything divided by itself equals number 1, cancels out. I'm left with moles of hydrogen, which is what we're trying to get in step 1. And now I can pick up my calculator, clear it, 8.765 divided by 2.02. And my calculator gives me this number. Times 10 to the 0, which means it's that. And obviously that's not correct. On test number 1, it'll say under your name, please use proper significant figures for all calculated answers. This is 4 significant figures. All non-zero numbers are significant. Zeros after a decimal are, so this is 3 significant figures. This is an exact number, plays no role. So which is lower, 3 or 4? And hopefully you pick 3. So you need to round this off to 3 significant figures. Keep the 4, keep the 3, keep the 3, use the 9 to round off. Is that 5 or higher? Yes, I'm going to drop all that, increase that by 1. And the correct answer for step 1 is 3.33 moles of hydrogen. Now, one thing I forgot to mention from the previous example, and I won't do it now, but I'll do it when I grade the test. there's two ways of rounding off for a multi-step problem like this. One way is to round off at each step, which is how I like to do it. I've done it where I've calculated for chemical companies amounts that we're dealing with $250,000 in chemicals. You don't want to make a mistake when you're dealing with $250,000 of somebody else's money, the company, because if you do, you probably get fired, and that never happened. But you don't want to. Or there's the other one, you round off at the very end. And different chemists do it different way, and you get essentially the same answer. But sometimes you might get different answers. On my test, I will calculate both answers, rounding off at each step, rounding off at the end. And both will be correct. Even though I'm a round off at each step guy, I'm not going to force you to do it my way. See what a nice person I am? Let's get back to our problem. We now have 4.33 moles of hydrogen. Are we done? No, we're trying to get the grams of ammonia. So now we have to do step number 2. And step number 2 is convert moles of A, in this case hydrogen, to moles of B, what we're trying to get to. Well, moles of A, we just figured it out right here. And what's B? Well, if we go back up here, we're trying to get the grams of ammonia. So B, what we're trying to get to, molecule, is ammonia. So we want to get to moles of ammonia. And now we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of this ratio. Whatever we're trying to get rid of goes underneath. And now I'll write those in. And notice I'm having, where do I get a ratio of moles of one compound, ammonia, to moles of another compound, hydrogen? From the balanced chemical equation. And this tells us 3 moles, remember the coefficient, the number of in front of the chemical symbol, 3 moles of hydrogen react when there's no coefficient, 1 mole of nitrogen to make 2 moles of ammonia. And the number in front gives us a molar ratio. And for this, we need, what's the relationship between moles of hydrogen and moles of ammonia? For every 3 moles of hydrogen, we make 2 moles of ammonia. For every 3 moles of hydrogen, we make 2 moles of ammonia. And that's where we get the numbers. Again, from the balanced chemical equation, you look at the coefficient in front, and that's molar relationships. For every 3 moles of hydrogen, we make 2 moles of ammonia. These are exact numbers. Now, before I pick up my calculator, see, I don't have it in my hands yet. I'm gonna, oh, that was an awful joke, sorry. But anyways, I will check my units. Notice moles of hydrogen divided by moles of hydrogen. Anything divided by itself equals number 1, which means it cancels out, cancels out. I'm left with moles of ammonia, which is where I want to get to. So now I can pick up my calculator. Times 2 divided by 3. And my calculator gives me this answer. I won't write all of it. It's 10 to the 0. Oh. So you don't need an exponential here. All right, come on.
I think it should be 4.34 when we round up, not
Can I do
4.
it backwards? Hold on,
Okay.
let me do something first. Uh-oh, hold on. Why is my pen died on me? Hold on 1 second. My computer is slowing down today. All right, we're back in business. I don't know. Sorry about that. My computer just burped on me. All right, let's get back to this and check that I did that correctly. 4.33 times 2 divided by 3. Now I have the right answer. If you're having trouble with your calculator, come to my office hour. I'll be more than happy to help you with something like that. All right, now we have to round this off to what? This is 3 significant figures, exact numbers. Round that off to 3 significant figures. Keep the 2, keep the 8, keep the 8, use the 6 to round off. It's 5 or higher, and that would be 2.89 moles of ammonia. And one of the things, Anna, you just asked about, what if you make a mistake at this point with your calculator? Well, if you have things set up right, and I say, oh, it's a math error, this is 10 points, I'll only take off 1 point for a math error. If you don't show your work and you put down the wrong answer, you get 0, zip, 0 points. So it always pays to show your work on my test. All right, so we're at step 2. We just calculated moles of ammonia. Are we done? And the answer is no, because we want to get the grams of ammonia, and we need 3 steps. So now, what is step 3? Well, you look at important information, moles of B, in this case, that's ammonia, to mass, which is grams of B. So now I will need step number 3. Moles of B to grams of B. And how do we do that? Well, what's B? What we're trying to get to, our final answer, we go way back up here, that's ammonia, NH3. And here, we have just figured out moles of ammonia We want to go to grams of B, in this case, B is ammonia. And now I'll use my good buddy, my good friend. Unit analysis, whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And my computer. We're back again. All right, now I should be able to write it in. And where do we get these two numbers? 1 mole of a compound equals the molecular weight of that compound. I'll write it over here, molecular weight of ammonia, which we've already done. So I'll do it real quick. 3 hydrogens, 1 nitrogen. I'll move this down here. To the proper significant figures, the molecular weight of ammonia is 17.0. So for every 1 mole of ammonia, I have 17.0 grams. And now before I pick up my calculator, moles of ammonia divided by moles of ammonia cancel out because anything divided by itself equals number 1, cancels out. I'm left with grams of ammonia, which is my right answer. Unit-wise, I'll clear my calculator, put in 2.89 times 17.0. I get this number. But this is 3 significant figures, exact number. Therefore, lowest 3 is 3. Round this off to 3 significant figures. Keep the 4, keep the 9, keep the 1. Use that to round off. It's 4 or less. And the correct answer is this. Let me write that 10 better. And that's your final answer. And let's go through this again. We're asked how many grams of ammonia are made when you react that amount, 8.765 grams of hydrogen, with an excess of ammonia. Now here, what are we being asked to find? Grams of ammonia. We're given grams of hydrogen. We're also given the balanced chemical equation. And we need 3 steps. In step 1, whatever we're given in weight, that's mass, which is hydrogen, we convert to moles of hydrogen. And now you see why earlier today I reviewed these types of calculations, because you need them all in this problem. And here, grams of hydrogen, moles of hydrogen. Remember, use unit analysis. 1 mole of a compound equals the molecular weight. That's where we get to 2.02. And the number you get is 4.33 moles of hydrogen. But we're trying to get the grams of ammonia. We need 3 steps. Second step, you have moles of A to moles of B. Moles of A was what you just calculated, hydrogen. B is what we're trying to get our answer in, ammonia. Eventually grams, but in this step, moles of ammonia. Now you use your good buddy, your good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we get a relationship of moles of one compound to moles of another? From the balanced chemical equation, the coefficients show us molar relationships. 3 in front of hydrogens means 3 moles of hydrogen. No number is 1. 1 mole of nitrogen makes 2 moles of ammonia. And for this problem, we need to know for every 3 moles of hydrogen, you make 2 moles of ammonia. And that's where we get 2 moles of hydrogen, or 3 moles of hydrogen make 2 moles of ammonia. These are exact numbers, 3, 3. We now have 2.89 moles of ammonia. But we have to get 2 grams of ammonia. That's why the question mark was there. At least that's what I use. And we need our third step. And our third step is moles of B, in this case, B is ammonia, to grams of B. And here we start out moles of ammonia. We want to get the grams of ammonia. And whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And units cancel out. Where do we get this ratio? 1 mole of a compound equals the molecular weight of the compound. The molecular weight is the sum of atomic weights. 3 hydrogen, 3 times the atomic weight of hydrogen, 1.01, 303. 1 nitrogen, atomic weight, the 3 significant figures of nitrogen is 14.0. Add them up, use proper significant figures for addition, and you get 17.0. And the final answer, 4.91 times 10 to the first. And that's how you do it. So we just did this. We did our practice. And as I say here, which we went through, remember 1 mole of a compound equals the molecular weight of that compound. And the coefficient of a balanced equation represent molar quantities. And there are practice problems for this. Now, let's talk about calculating the amount of a substance. Well, we've already done this. This is also called limiting chemical reactants, which this book doesn't use, but I do. All right. Special effects time. Hold on 1 sec. There we go. All right. Everybody see the red pen I have in my hand? Good. Now, let's assume you make these and your company buys the pen and buys the cap. And what your company does is put them together and sell the whole pen. What if you have 5 of these and 10 of these? How many whole pens can your company make? Well, if you only have 5 of these, even though you have 10 of these, this is going to run out before you use all these. So this is limiting how many total pen units you could make. If you have 5 and 10, you can only make 5. Well, what about in chemical reactions? And let's look at a problem. Now, I could make it super hard, but don't tell anybody, but I won't. All right, everybody see that 5 points? You're given a balanced chemical equation and you're asked how many moles of water are made, excuse me, if you react 10 moles of hydrogen with, I burped again, I'm sorry, 3.00 moles of oxygen. So what are we being asked to find? Moles of water. What are we given? 10.0 moles of hydrogen and 3.00 moles of oxygen. Well, how do we begin? Well, if you notice, this is a unique problem. You're given the moles of each reactant. Remember, at the base of the arrow, these are the reactants. And you're being asked to find moles of product. In this case, water. So what do? Well, you look at important information, limiting reactants. Now, the best way I found to do this is determine the number of moles of product using the moles of each reactant. And the lower number is your answer. Again, you have to do two things, determine the number of moles of product using each reactant. So how do we do that? To determine the number of moles So for hydrogen, 10.0 moles hydrogen, and we want to get moles of water. That's our product. And we'll use unit analysis, your good buddy, your good friend, whatever you're trying to get to, goes on top. Whatever we're trying to get rid of goes underneath. And where do we get these numbers? From our balanced chemical equation. For every 2 moles of hydrogen, you make 2 moles of water. And now moles of water, hydrogen divided by moles of hydrogen cancel out. These are exact numbers, and I can do this in my head. The answer would be 10.0 moles of water you'll make. Now that's for one. You'll have to do the same for oxygen. Again, for each reactant, you find, hold on 1 second. My computer, I think I know what's wrong. Hold on. Let me do this. Nope, that's not what I want. That's not what I want. We might go a minute later than normal. I think this should fix it up. For those who don't know, CCleaner is a great product. Oh. All right, let's just go ahead and do this without the red pen. Nope. All right, whatever I'm trying to get to unit-wise for the second calculation. Wow. Goes on top. And whatever we're trying to get rid of, moles of oxygen, goes underneath. And you can't see it. Let me rewrite it. From the balanced chemical equation, 1 mole of oxygen makes 2 moles of water. And moles of oxygen divided by moles of oxygen cancel out. 2 times 3, 6.00. Now, for this one, you look at both of these, and the lower number is your answer. In that case, our answer is this 6.00. And with that, I've just run out of time. All right, with that, I'm going to say gang gesund, goodbye now. And don't forget, I have my office hour, and have a nice rest of the week. And I'll see you on Monday unless you come to my office hour. Bye now.